We are going to look now at what is called a chi-square distribution. So first up is this is the Greek letter chi. It looks like an X in a way, but it's got a longer tail. And it's called chi-square because we are going to square it. So that is chi-square. And the chi is spelled with a C-H-I. And the distribution looks like this. Now it's squared, so everything starts at 0. There's no negative values, like in the student's t and the z distribution. Those were symmetric about 0, so we had both positive and negative values. This one is positive only, starts at 0, goes up quickly, and then slides back down like this. So it's skewed to the right. And actually the curve that you get depends on the number of degrees of freedom. So this one here might be, let's say, df. Degrees of freedom might be like 4. If the degrees of freedom goes up, the curve gets a little bit less skewed like this. This might be, say, degrees of freedom equals, say, 8. This one here might be degrees of freedom equals, say, 12. And as the degrees of freedom increases, degrees of freedom goes up, the curve becomes more bell-shaped. So we just took a look at the chi-square distribution, which we are going to use right now in a test called goodness of fit. When we sample something, the results obtained in those samples may not agree exactly with the theoretical results expected according to the rules of probability. What we see in our samples may not agree exactly with what we expect. So when we take samples, we have observed frequencies. Let's call them like O1, O2, O3, the first observation, the second, the third, so on, dot, dot, dot. And I'm going to run this up to O sub k, like the kth observation. So we have observed frequencies O1, O2, O3, dot, 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 up to O sub k, and corresponding expected frequencies. Let's call them, I'll use capital E, E1, E2, E3, dot, 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 up to E sub k. Now we wish to know whether the observed frequencies differ significantly from the expected frequencies. What we observe, does it differ significantly from what we expect? Now, in an experiment in which you have n independent trials, the expected frequency is found this way. The expected frequency is n, the number of trials, times p, the probability of success on a single trial. Now, we did this before when we looked at binomial probabilities, and we saw this, that p was equal to, remember we had like r over n? Okay, I'm going to write it now like this, a little bit more general. So it could be now that p is equal to, because if you have more than just one success, it could be like this. x1 plus x2 plus dot, 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 plus x sub k over n1 plus n2 plus dot, 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 plus n sub k. Now we need a measure to tell us the discrepancy between the observed and the expected frequency. And that measure is going to be this chi-square. And here's how we're going to write it. Chi-square is this. It is the summation, right? So we're going to add things up. And what are we adding up? We're adding up these fractions. All right, so you take O minus E, that quantity, and you square it, right? Because everything is squared, all over E. Now just E, not E squared. And we write this sum. The sum goes over all the O's and all the E's. And in this case, the degrees of freedom is k minus 1, where k is the number of events. So this chi-square actually looks like this. If we were to write it out, it would look like this. you sum up these things. Take the sum of these things. Now, these things look like this. It might be like this. Okay, O1 minus E1 squared all over E1. This is the number that you observe on the first trial minus the number you expect on the first trial squared all over the expected number on the first trial. Then plus O2 squared, O2 minus E2, that squared, all over E2, plus dot, dot, dot. You just run them through all k events. O sub k minus E sub k squared. Oh, let me write that so it's readable, or more readable. All over E sub k. And just one thing to note here is that this distribution works best when the expected number is greater than or equal to 5. So the expected number in each case has to be greater than 5. We are going to use this chi-square as our test statistic in testing a hypothesis about how well a set of data fits a particular model. Do we have a good fit or do we not have a good fit? Now, I know this is one of those things that seems a little bit vague, and it probably is right now, and we'll clear it up when we do an example, and I hope it all comes together. Well, speaking of examples, here's one right here. It says the type of household for the U.S. population for a random sample of 411, so I wrote that down. All right, so the type of household for the U.S. population for a random sample of 411 households from the community of Dove Creek, Montana, are shown right here in the statistical abstract of the U.S. So apparently there are 5 different types of household: married with children, married no children, single parent, one person, and other, roommate, siblings, etc. And then the table shows that 26% of all households in the U.S. are married with children. 29% of all households in the U.S. are married no children, and so on. But then in our sample of 411 households from Dove Creek, Montana, what we have, here's what we observe. We observe 102 households are married with children. We observe 112 are married no children, 33 single parent, 96 one parent, one person, and 68 other. Our question is this: how well does the distribution of households in Dove Creek fit the distribution of households in the entire U.S.? Are they the same? Are they different? To see if we have a good fit or not, we will use the chi-square, this one here, statistic to measure the discrepancy between the observed frequencies, here's our observed frequencies, and the expected frequencies. So I think we better get the expected frequencies. If Dove Creek really does fit the model of the entire U.S., how many of each household type do we expect to see? For example, we're seeing 102 married with children. How many do we expect to see? Well, we noted here that the expected number is N times P. So what do we expect for married with children? I'll do it like this: expected married with children. Okay, if I write N times P, well, N is 411, and what is P? All right, P, this should be the percentage. I'm up here at the left here. This should be the percentage of married with children. That's 26%. All right, so this is 0.26. And my calculator says that that is 106. 106.86. Now, what about the next one? What's the expected number of married no children? Okay, well, that's going to be N times P again. Now, N is 411, right? We're making 411 observations, and 29%, according to the U.S., 29% should be that household right there. And that comes out to 119.19. 119.19. Now, the expected number of, what have we got here? SP, single parent. Well, we still have 411 observations, right? We're observing 411 households from Dove Creek. And the U.S., in the U.S., it says that 9% are single parent, so this should be 0.09. And computing, I get 36.99. And then the expected number of OP, one-person households, all right, are still 411 observations, but this is 25%, 0.25, right? So that turns out to be 102.75. And finally, the expected number of other, how about just O? That's going to be out of 411, we should be observing 11%, 45.21. Now we are going to run a goodness of fit test, so we need degrees of freedom, and degrees of freedom for goodness of fit is K minus 1, and just to remind myself what K is, it is the number of classes, and I spell it that way just to remind me. K is the number of classes minus 1. Now, in the number of classes, we have, 1, 2, 3, 4, 5 classes. So 5 minus 1 is 4. We've got 4 degrees of freedom. I ran out of room on that page, so I just transferred everything to this page here. So what I've got is here. These are my observations, my observed values, right? How many did we observe out of our 411 people in Dove Creek? We observed 102 married with children. We observed 112 households married without children. 33 households we observed single parent, and so on. And here's my expected values I got by N, 411, times the percentage given in the table. Now I'm going to compute the value of my test statistic, chi-square, and I always put a little star on it to remind myself that I've actually computed. This is a computed value, not one I found in a table. All right, so chi-square star, here's my formula. So I'm going to add up a bunch of these. O minus E squared over E. So here's the first one, 102, right? I'm just following up here, right? 102 minus 106.86 squared divided by the E, the 106.86, plus then the next one. Next one is, all right, 112 minus 119, so it's the O minus E, the O, 112, minus the E, 119.19, squared, divided by the E, 119.19. Okay, so I did that for all 5 of these. So I wrote them all out by hand. Then I did each one individually. I rounded off a bit here. So I've got the first, the second, the third, the fourth, and the fifth. Now you can see these discrepancies are pretty small here for the first 4 anyway. You know, like 22% we're off about 43% here. We're off about 28% here. We're off about 44% here, but look over here. We're way off here. We expected to see how many? We expected to see, these are just other households in Dove Creek. We expected to see 45. How many did we really see? 68. So I added all those up, and here's my chi-square star value right here. All right, there's my chi-square star. Now, for sure, the calculator will do this for us, right? Could do all this stuff on the calculator, and we will. It's like I've got a list 1, my O's. I got a list 2, the E's. I just put those in and then go find chi-square goodness of fit on the calculator. It does all of this work for us and will come out with a p-value. But I'm going to use, first of all, the critical region approach, because I think if we see this, it gives us an idea of what it is we're measuring. You know, I'm trying to measure the discrepancy between what I observe and what I expect. And if you can see these minus signs in here, you can tell, oh, minus signs, minuses, we're doing a difference. I'm finding how much one number differs from another. So I can see that going on here. If I choose to do it on the calculator, I don't really have a feel for what it is that we're doing. Now, I'm doing this by the critical region approach. Table in the back of the book gives us the chi-square table. So this table right here, this is the chi-square table. I just got it out of the back of the book. And we need to find 4 degrees of freedom. Now, degrees of freedom, right down the left column here, there it is, 4 degrees of freedom. And we're doing this at the 0.05, that's what the problem says, use alpha equals 0.05. Now, the table is set up like this. The table is set up to read this way. I'll draw a picture of it here. Here's the chi-square curve, and the area that they're giving us here is in the right tail. All right, so this is going to be our alpha. And an important note here, since we're squaring everything, this is 0. Chi-square is always a right tail test. We don't do a two-tail test or a left-tail test. Always a right-tail test. Let's look for our alpha at, okay, I'm over here, 4 degrees of freedom. Alpha is 0.05. Where is it? Right here. Okay, 0.05. So it looks like our critical value here is 9.49. All right, that's our critical value. So the chi-square value, the critical value, is 9.49. All right, that's our critical value. That's our reject value. All right, that's our reject value. Let's set up our test. This one looks different than anything we've done before. We have a collection of percentages. I've got a model here, and I want to test whether this model is the same as the observed model. So either the percentages are equal or they are not equal. Now, just for convenience, I'm not going to write a bunch of not equal signs right here. Why don't we just say not equal? I either have these percentages or I have other percentages. Now, step 3, I've got 3 parts to mine. Step 3, part 1, is to get the right test statistic. Now, we've already been using this, but let's write it here. It's chi-square equals the sum of these, right? The O minus E squared all over E's. That's what we're going to use to measure the discrepancy between the claimed values, or the standard, and ours, our observed values. So that's step 3, part 1. We've already done this one, right? And then step 3, part 2 is to choose alpha. So why don't we say let alpha equal 0.05. Step 3, part 3, this is where we're going to get the critical region here. Now, this is a chi-square test, so we'll draw a chi-square curve. All the area goes into the right tail. That's our critical value, and that's the one that we just found. And that was 9.49. Now, there's our 0. Now, remember what this 9.49 is? That's our critical value. That means that we know there's a difference between the observed values and the expected values. But how much difference are we willing to accept? If there's 0, there's no difference, we're willing to accept that. If there's as the difference gets bigger, we're willing to accept until a certain point. How big a difference are we willing to accept? Well, this is what we're saying. That's our cutoff point. So if the difference gets any bigger than this, we're going to reject H naught, right? Because we're actually seeing the observed values. We believe what we see. We will reject here at that critical value. Now, we computed this. It took us a while because we had a lot of computations to make, but that came out to, when I rounded it off, 12.86. So now in step 5, we're going to compare the chi-square star value to our critical value. So we can just go back to our drawing and see where we're going to land, right? Here's 0. Here's 949. Our compute value is 12.86. So just on the number line, 0, 9.49, 12.86 is out here. So I'll do a line, draw a line, and I'll put a star because to me that star matches the one on my critical value. So we're out here in the critical region. And in that critical region, what I'm going to do is I'm going to reject H0. And we are rejecting H0 because we don't believe we have a good fit between the U.S. household model and the Dove Creek household model. So let's write our conclusion as we typically do. Add alpha equals 0.05. This sample indicates, all right, so pretty standard. This sample indicates, now I'm just going to go back and use the wording in the problem. The two distributions don't match, so that's just what I'm going to say. The distribution of households in Dove Creek does not fit the distribution of households in the U.S. Now let's do this using the p-value method strictly on the calculator. The p-value method on our TI-84s is press stat, right? So you go to stat, select number 1, edit, brings up your lists, L1, L2, and some others, but we need to clear these lists. So do you remember how to do that? Take your cursor, get it over into list 1, and then up arrow so that the cursor is exactly on, right, that's highlighted, on L1. Press clear, and then enter. All right, so get the cursor on L1, press clear, and then enter at the bottom. Then cursor over to L2, get the cursor on L2, so that's highlighted, press clear, and enter. So those two lists should be clear now. So get your cursor back into L1. So we're in L1, L2, and now we're going to just put the data in. So let's type in our data here. So it's 102, enter, 112, enter, 33, enter, 96, enter, 68, enter, right arrow over to L2. Well, now in L2, we don't have these values yet. Remember, we already have them because we did it the long way, but if we're just starting out using the p-value, we're not going to have these values. So have the calculator do it for us. Remember what it is. It's n times p. So n in every case is 411. So you're going to just type in 411 and then times, all right, now this is 0.26. All right, so you type in that and press enter. And when you press enter, it comes back and actually computes it for you, and it will say 106.86. All right, then you've got it entered. So then you come down to the second entry, 411 times, now this percentage is 0.29, 0.29. And when you press enter, it comes back with 119.19. Then 411 times this percentage, which is 0.09. Press enter, you get 36.99. Then you get 411 times this percentage, which is 0.25. And that gives you the 102.75. And then finally, you hit the 411 times this percentage, which is 0.11. And that gives you the 45.21. Now we're ready to go. So press the stat key again, over to tests, and then you can scroll up or down, but it's item D. So you scroll to D where it says chi-square GOF, goodness of fit test, and choose that one, all right? So you scroll down till you get to it, you press enter, and what comes up is observed, and it wants a list here. What list are your observed values in? Well, we put those into L1, all right? So how do you get to L1, right? So we're going to type in L1. How do you get there? You press second and then the number 1, right? Second and 1. Enter it. Then L2, right? This is our expected. We put into L2, so second, the numerical key 2. Now, it should be coming up with degrees of freedom 4 because it knows how many classes we have already. So my calculator shows, now it just says chi-square, but I know it's chi-square star because it's the computed value. It's 13.016. Now, when we did it the long way, we got 12 point something, but those numbers were rounded off, so this is more accurate. So what's the p-value? The p-value is 0.01119. Okay, so how about this? P is equal to 0.0112. That's the p-value I'm going to use. So now what do we do? Reject, fail to reject. All right, so I'm going to compare P to alpha. Right now, P is 0.0112. Alpha, you remember, is 0.05. Now this is 1.1%. This is 5%. This is less than. All right, so what do we do if it's less than? If it's less than, I think, all right, this is a less than, so I think small, and it's a small probability. Now, if it's small probability, then it's an unlikely event. But I'm seeing it, and I don't believe typically I see things that are unlikely. So I'm seeing an unlikely event, so I'm going to reject H naught. And then I'll just state my conclusion here. Same as we did before. At alpha equals 0.05, this sample indicates the distribution of households in Dove Creek does not fit the distribution of households in the U.S.